get a free ODE. And before I forgot to tell you about the ODE clown. The clown you see up there, that's the clown you will see whenever we publish an ODE, because for me this kind of symbolizes the feeling you have when finally, after months of work, something actually works. So, yeah, what you can now do is you can piggyback your actual frame, the frame that you once sent to the destination, inside a large frame, and then the first header will be checked and the second one will not be. So we get to pass through the firewall. There's a slight difficulty with this, but it's not really a difficulty. The CRC checksums must match, but since we have this part of the packet which can be discarded, we can actually put whatever we want into there. And if we can set 4 bytes arbitrarily, we can just adjust the checksums. So this is not really a problem. It's not MD5, it's CRC32. There are limitations. Default MTU, it does not work, but for all other MTUs it does work. So, now we've bypassed the firewall, at least in one direction. And now we can go and attack Squid. Next goal, we want to be able to supply updates from update.adobe.com or provide the start page for citibank.com, something like that. Poisoning the cache. What's the time? Ooh. I'm going too fast again. Okay, poisoning the cache. The interesting thing about the Squid web cache is that it's actually not just a web cache, it's also a DNS cache. This gets obvious because you can actually tell it to get foo.bar and not just to get some IP address. So it caches DNS for a max of 24 hours, so that's enough for us to want to attack it. And the authentication used for DNS has been criticized over and over again. Those are just 32 bits, really, which we have to guess. There's the source port, the UDP source port, which is not even part of the DNS message. And then there's a transaction ID. So now, even in the face of popular DNS security research, Squid chooses to implement this by itself. And what it does is it opens a single UDP socket to transmit all DNS queries. Okay, so this is random. This is a random port. That's nice. But it's static. It remains the same over the entire lifetime of the cache. And that's not a wise choice, because by default you can actually scan for this. Because if you send the UDP datagram to a closed port, you get an ICMP port unreachable by default. Otherwise, you just don't get any response, so you can see whether the port is open or not. But of course, we're assuming that we can't do this. Because if we assume that we can do this, which we probably can in reality in many networks, then it's going to be boring again. So we can't do this. So here are the implicit assumptions Squid is making, and this is actually the interesting part. See, first of all, Squid is protected from IP spoofing if layer 2 and layer 3 actually provide this. Then Squid also expects that you filter ICMP port unreachables, because if you don't, the source port's scannable. And then it generates its own transaction ID of 16-bit. And that's all the security provides itself. So trust, the security is actually handed off to other layers. And that's the dangerous part. So for the attacker, it looks like this. We need to bypass layer 1 and 2, layer 2 and 3 filters. Done with the Ethernet exploit. Now, we need to determine the source port, even if we can scan for it. And that's what we're going to do now. So to do this, we break the nut. Because you cannot assume that the source port will actually stay the same if your packet is transmitted over a network address translator. So here's what it normally looks like. Normally, you have your internal IP address, 192.168.2.3, and then it's mapped to an external IP address, 80.80.80.80. And the source port stays intact. There's no reason to change it, simply. But now what happens if two different hosts inside the local area network want to use the same source port? Well, for one of them, it's not a problem again. The IP address is mapped, but the port remains the same. But for the other, we have to do something. We have to kind of handle the collision that arose. And we do that by using the static port 1024. But that's not the bug yet. So, first part is the collision, which is handled correctly, like I just showed you, the first two rows. And now the bug. If you now send a packet on that same source port, but to another host, to a host somewhere on the internet, it will actually handle the collision even though there is no collision. So now it discloses that there was a collision earlier. It tells you that the source port was actually already used to connect to the DNS server. So how do you exploit this? I know this is not that easy to understand on the first explanation. So this is how you exploit it. Maybe this will be clearer. First, you send a packet to the DNS server with a given UDP port, the port that you want to scan, source port. Now you send a packet to that other host that you control on the internet with the same source port. And now at that other host, you can check whether the port is the original port or 1024, in which case this port was used to contact the DNS server. So this is how you can scan the nut for the source port used by Squid. All right, done. Last step. We need to reply with the correct TX ID before the DNS server does. I'm going to show you one possibility which actually did not work out, but it's so beautiful I just can't leave it out. This is a design bug, kind of. It can work, but not with default configurations. What Squid does is really funny. When it is waiting for a DNS response, it will constantly call receive from, give me the next packet please. But when it's not waiting, it will just sit there and sleep. And you can fill the queue. So you can place your guesses in the queue before the race starts. Yeah. I will gladly store your guesses in kernel memory until the race begins. First thing into the race, we'll consider your guesses, sir. So the default queue size, at first looks pretty big. So you start calculating and writing down stuff, and it's like, oh, I do 20 tries, and I'm at 50% chance without knowing anything. But in practice, that doesn't work because of all of the overhead you have. This queue actually stores complete frames because, of course, when you receive frames, you don't really want to do a lot of copying. So in the end, you end up with 50 DNS responses you can place in the default queue. So that's nothing. You can't work with that. So I tried to determine that upper bound. I wanted to know how much can I place in practice by sending header-only packets, which then gave me this DOS for free. So you're stuck. It's right before Christmas and you're stuck. But then you realize that there's a huge difference between